So let's talk a little bit about stability of systems, in particular time-invariant linear systems. And there are actually several notions of stability, and you will probably encounter a couple of other definitions besides the one we're going to talk about today, but this is perhaps the most common one. And we said that the linear system is called input-output signal stable, or just stable, if it maps bounded input signals to bounded output signals. So somehow this corresponds to the idea that a stable system can't add an infinite amount of energy to the input signal. If you imagine that these input signals sort of measure voltage of an electric signal, something like that, then you would expect that if you have a system, that physically realizable system that actually works for a long period of time, the output signal can't really be arbitrarily large, because that would blow up the system from the sort of the mechanical or electrical system that this corresponds to. So stability is usually something you want. Sometimes you are aiming for unstable systems, because you can, for example, want to have amplification that's unbounded. But if you're going to run an unstable system for a long period of time, you need some dampening control added in, otherwise things will blow up. Okay, anyway, let me give you an example. A nuclear power plant is inherently unstable, but thanks to the control mechanisms that keep the nuclear fission reaction in check, you can still most of the time count on a nuclear power plant to run for a long period of time without blowing up. At least that's what we hope for. Okay, let me give you an example. One of our favorite linear time invariant systems is the differentiator that takes an input signal f to the output signal f prime, the derivative of the input signal. This is not a stable system, because you can find functions that are unbounded but have an unbounded derivative. It might take a little bit of effort to cook up such an example, so let me give you one. F of t equals sine of t squared. It's clearly bounded, because sine of anything is between -1 and 1. But the derivative of sine t squared, it's 2t times cosine of t squared, and it's not hard to see that this is an unbounded function. The cosine factor oscillates between -1 and 1, but thanks to the factor 2t in front, the amplitude of this oscillation will blow up eventually. So this is not a stable system. Now, if you have a linear time invariant system, then you have an impulse response, and we already know that the impulse response contains more or less every piece of information there is about the linear system. So shouldn't come as a surprise that it's fairly easy to tell whether a system is stable if you know its impulse response. And this is the condition. If you have a linear time invariant system with impulse response h of t, then the system is stable if and only if the integral of the absolute value of h from negative infinity to infinity is finite, meaning that this improper integral should converge. This is also sometimes called that h is absolutely integrable, or if you know a little bit of technical mathematical jargon, that's the same as saying that h is in the Lebesgue space L1. It doesn't really matter if you've seen that notation before or not. But anyway, let me give you at least a sketch of the proof of this, because it's not very difficult and it gives you some information. So assume that you have an impulse function, an impulse response that integrates to something finite, and that f is any bounded input signal. Then we want to show that the corresponding output signal is also bounded. But we know how to compute the output signal, right? It's the convolution of the impulse response and the input signal. Or if you compute it at some particular point in time, you get that the output signal value at the point t can be written as an integral of h of t minus tau times f of tau d tau, where we integrate from negative infinity to infinity. And if you put absolute values quality, but then we can estimate the integral, because since we assume that f is a bounded input signal, that means that the modulus of f of tau is bounded by some number, namely the maximum value of the modulus of f of the tau. And we can pull that out of the integral, and we can use the triangle inequality for integrals to push the absolute value sign inside of the integral. So the absolute value sign there, the absolute value of that integral can be estimated by the maximum of the absolute value of f times the integral of the absolute value of h of the real line. But both of these are finite numbers independent of t. So that means that we can find some constant c such that the output signal is bounded by c for every value of t. In other words, we've shown that the output signal is a bounded function. So that was one direction, assuming that we have an impulse response in L1, then the system is stable. How about the other way around? Well, for the other way around, we need to use the fact that the system is stable, in other words, that it maps bounded input signals to bounded output signals. So that means that we can see what happens if we plug in any old bounded input signal. And in particular, we're going to use this strange guy here. We're going to define a function f of t equals, that's equal 1 if h of, well, sorry, that should be h of minus t is positive, and it's negative 1 if h of t is negative. So we pick up the sign of h of minus t. Now, of course, this is a bounded input function. So in particular, the corresponding output function, output signal s of f, is also bounded. And for example, if we compute the output value, signal value at t equals 0, this is the convolution of h of f at t equals 0, which is just the integral from negative infinity to infinity of h of minus tau times f of tau d tau. And since we chose f in a really clever way, that product h of minus tau times f of tau, that's exactly the same thing as the absolute value of h of minus tau. Because we leave h of minus tau unchanged when it's positive, and we flip the sign when it's negative. So that means that what we get is actually the integral of modulus, or the absolute value of h over the whole real line. It doesn't matter if it's a minus tau or not in that integral, of course. And this must be a finite number, since SF is a bounded function by assumption. So that means that we also shown the other way around. And in some sense, this is the worst possible input signal. So this is the input signal that exactly matches the sign of the impulse response, in the sense that we expect an amplification all of the time, but this is still the worst possible. Even with this worst possible input signal, we get something finite. Okay, let me also finish this recording with a few words about causality. That's something we've already seen, at least in passing, in one of the previous videos. And let me remind you what it is, and for at least let me write down a proper definition. I never did that last time. So a causal system, the system doesn't have to be linear or time invariant. A causal system is a system that, if we take any fixed point in time, t0, and every pair of input signals, f1 and f2, that agree for all time up until this particular point in time, t0, then the corresponding output signals should also be equal up to this point in time. So intuitively speaking, this says that the system cannot look into the future. So the value of the output signal can only depend on the value of the input signal now and at previous points in time. Of course, for physically realizable systems, this is always the case. Nobody has ever been able to build a time machine. You will probably be enormously rich if you manage to do it. But there are situations where you would like to study non-causal systems. For example, some of these the perfect filters in analog electronics, for example, correspond to non-causal systems. I'm not going to go into detail there, but you might wonder why do we care about non-causality at all. Sometimes it actually matters. Okay, let me just finish up with a simplification here. If you have a linear time invariant system, this is easier to check, and you can convince yourself that the condition on the previous slide is actually equivalent to saying that the system maps causal input signals to causal output signals. And here a causal signal, that's a function that's 0 for negative values of t. In fact, if you know the impulse response of the linear time invariant system, this is even easier to check, because as an exercise you can prove that causality for linear time invariant systems is equivalent to saying that the impulse response itself is a causal function. So the impulse response should be 0 for negative values of t. That's if and only if the system is causal. Okay, let's finish this